of September and recall that given a Q, we work in the category of Q vector space for the time being. Q vector space. Q is because I want to use the minimal field, but of course you can use the complex number, the real numbers, it is harmful. The vector space V, dimension of V equal to n, one may associate an algebra wedge V with the product. This is the support of the algebra, and this is the product, the wedge product. And one may associate an algebra, wedge V wedge, where wedge V is by definition the direct sum for I bigger than 0 of wedge IV, where wedge IV are vector space, we will recall, and where wedge 0V is by definition the field, wedge 1V is equal to V, and wedge 2V is the span of the element Bi wedge Bj such that I is bigger than j, bigger than 0, and n having set as a basis of V. Okay, so my vector space V has dimension n, and the basis I call B0, B1, Bn minus 1. I want to do just one more example that we did already last time, but because I don't want to lose anybody in the audience. Take example.
So, Ethereum.
Yes, there is somebody who wants to enter.
Martin, yeah?
Yes, let me see.
No, it's okay. You can keep writing. Just open your screen where you were writing just now.
Just a moment. Yes, I. Do you think I can keep writing when I am admitting?
No, there is no one. I just wanted to ask you a quick question, yeah?
Yes, please.
Yeah, you see that notation there. I'm finding it.
Just let me only to increase the volume because audio. Let me see output volume. Okay, say again.
Volume is fine. We can hear you.
Say again.
Can you hear me clearly then?
Yes, now better. Yes.
Okay. I was just asking about the notation. I'm finding that notation a bit confusing. That wedge V, which is your exterior algebra, right?
Yes.
Is it not possible to use a different notation for that? EV or something like that. Unless if it's classically, that's what is accepted. But I'm not seeing it very convenient. Because your exterior algebra, basically is the direct sum of those things, those exterior powers.
Yes. So.
Yes. So.
Yes, but it's a standard notation to use lambda. I think that on all books, this is the notation.
So, of course, we can agree to use another notation, but this is the standard notation in all the books, So wedge without, there are some people write like this, with the dot here, to denote that there are many, this is a graded algebra. And unfortunately, the official notation is wedge IV, which we could also invent another notation. But the reason I'm using this is because it's the one most of you will find in the literature. Okay?
But okay, it's fine. We can proceed.
Yes.
I would prefer EV or something, because to me.
Tell me again, what is the notation you were suggesting?
No, I would prefer an E there, where the wedge is.
The operation, you mean?
Yeah, on the wedge, on that wedge V, the one we are calling the exterior algebra, wedge V, right?
Yes.
I would prefer an EV on that.
Yes, you are complaining on the operation, right?
Not that one. The first one.
Yes, this one.
To put an E, to put a curly Metcalfe E.
Yeah, I understand what you mean. Yes, Metcalfe E, for instance. Yes, but this is not the standard notation, and
yes.
We can.
Yes, also for differential forms, it is used the wedge, and so this is
in differential geometry, for instance.
Yes. Yes.
Of course, we should not give too much importance to notation, more on the substance, but well, for the time being, we keep this. And I want to give you an example. Again, I take dimension of V equal to 5, so the basis is B0, B1, B2, B3, B4. Well, I want to be more precise, because if we decide, since V by definition is wedge 1V, and we want the index in decreasing order, we write like this. So this is the basis. It's strange. Everybody writes the index in increasing order and we use in the decreasing order. Very strange. Why you want to do this? You will see when we will work with the vector space which have infinite dimension. We have this basis, and then we want to figure out what is the exterior algebra. And the exterior algebra is, first of all, Q. Then there is the V, and then we have to put the wedge to V, where wedge to V, let's write the basis. Basis of wedge to V is equal to B1 wedge B0, B2 wedge B0, B3 wedge B0, B4 wedge B0, B2 wedge B1, etc. Are you able to complete this table? Please do it. So an element of wedge 2V is a linear combination of this expression. Then we have wedge 3V, which is easier, basis of wedge 3v is B2, B1, B0, then B3, B1, B0, then B4, B1, B0, then I must then we have B3, B2, wedge B0, then B4, B2, wedge B0, and finally B4, wedge B3, wedge B0, and B4, wedge B3, wedge B2. Then we count the basis element 1, 2, 3, 4, 5, 6, 7. Oh, for sure I forgot something. They should be 8, but B2, B1, B3, B1, B0, B4, B1, B0, B3, B2, B0, B4, B2, B0.
I think that is missing B3, B2, B1.
Sì, B3, B2, B1, and then there is also B4, B2, B1, and you complete and you find that the dimension wedge 3V is precisely the dimension choose 3. So this is 5 times 4 divided by 2 is 15, as dimension 15, this vector space. And if you want to compute the dimension of wedge 4V, you just compute the number of the basis elements. Here is even easier, B3, B2, B1, B0, and B4, B2, B2, B1, B0. Please complete, you will find that the dimension of this is precisely 5 choose 4, which is 5. Okay, and then there is wedge 5V, whose dimension is 5 choose 5. So the dimension of wedge V is the dimension of the direct sum wedge IV, I bigger or equal than 0, which is equal to the sum I bigger than 0, then the dimension of wedge IV, which is the sum I bigger than 0 of in this case 5 choose I. And well, you could say, yeah, and if I is equal to 6, then is the binomial 5 over 6. What about 5 over 6? This is 0. Why it is 0? It is 0 because recall the definition of the binomial coefficients. The definition is that n over k is equal to the coefficient of xk in the expansion of 1 plus x to the power n. This is the definition of the binomial coefficient. So 5 over 6, 5 choose 6 means compute 1 plus x to the power 5. what is the coefficient of x to the power 6? Is 0, of course. This is 0. But the sum of phi over I is the same as the expansion I equal to 0 to 5 is exactly the expansion of 1 plus 1 to the power 5, which is to the 5. Which means that the dimension of wedge V in our case, well, it means that the dimension of wedge V is 2 to the power n if n is equal to the dimension of V. Okay? Okay, and now I want to how to say, I want to give you a first example of something that I am planning to use very much with you during our research activity, which is this. We have seen a generating function. We have seen that the dimension of wedge Vn is equal to 2 to the n, where Vn okay. So we want to find a formula which says us the dimension of all the exterior algebra of vector space of any dimension, and the standard procedure in combinatorics is to consider
n there.
what?
N. That last expression.
Yes, Vn. Vn, it means the span of Bn minus 1 to B0. Okay? And the dimension is 2 to the n, as here in this case is 2 to the 5, because the dimension was 5. And then the trick I want to propose you, please say me, Martin.
No, I'm saying it's the same as the dimension of wedge Vn as well.
Exactly. I mean, I put n to emphasize that the dimension is n. Okay.
Yeah.
Okay.
No, probably you mean the dimension of Vm. So you wrote.
Sorry. N. You are right. Sorry.
Yeah.
Sorry. You are completely right. So we can consider the sum of the dimension wedge Vn over n factorial Tn, and this is 2Tn over n factorial, which is the definition of the exponential of 2t. So what does it mean, this expression? Of course, if I sum, if I take the direct sum of infinitely many finite dimensional vector space, these vector spaces, I mean this direct sum has infinite dimension, of course, but we can create what we call a generating function. What this equality says? This equality says that if I want to compute the dimension of wedge V10, this is equal to coefficient of t to the 10 of the expansion this is the coefficient of 10 factorial t to the 10 of the expansion of exponential of 2t. Okay, this is just one. Okay, so we will get used to this nice generating function. It's something new because let's say we can see some functions as a way to encode a lot of information. I mean, in exponential of 2 to the power t, the coefficient, what is the exponential to the power t? We wrote exponential of 2t, it means 1 plus 2t plus 2t square over 2 factorial plus 2t cube over 3 factorial, etc. Okay, so we know that the coefficient of t to the n is precisely the dimension of the exterior algebra of the vector space of dimension n divided by n. For instance, if I want to know what is the dimension of wedge V2, vector space of dimension 2, we look there. 2t to the square over 2 factorial is equal to 4t square over 2 factorial. We forget the 2 factorial and we find that you know, we forget because the 2 factorial is the trick. We put this n by n factorial the denominator. So what we found is 4. But this is true because wedge V2 is equal to Q, which has dimension 1, is equal to V2, which has dimension 2, and then there is wedge 1 V2. Wedge 2 V2. A wedge 2 V2 has a basis, the basis B1 wedge B0 has dimension 1. So you see, this has dimension 1, this has dimension 2, this has dimension 1, 1 plus 2 plus 1 is 4. So that exponential of 2t encodes all the possible dimension of all the exterior algebras. This is one of the easiest example of generating functions. We will see more. And I'm going to do something something very concrete with you now. I recall just an exercise, because if a wedge V is an algebra, it means that we can perform product. I want to give you an example. For instance, compute B2 wedge B1 plus B3. Why not? It's not homogeneous. This belongs to wedge 2V. This belongs to V, which is the same wedge 1V. Wedge 2B1 wedge B3 wedge B4 plus B4 wedge B2. And what we do? We do distributive law. B2 wedge B1 wedge 2 B1 B3 B4. And we put the 2. B2 wedge B1 wedge B1 wedge B3 wedge B4. And then we associate this with this one. plus B2, wedge B1, wedge B4, wedge B2. And now we associate B3 with the other one. 2, B1, B3, B4, and then B3, wedge B4, wedge B2. Now I see that here B1 and B1 is repeated, and here B2 and B2 is repeated, and here B3 and B3 are repeated. Then I cancel, and I have a B3, wedge B4, wedge B2, which is the result. The result is B3, B4, B3, wedge B4, wedge B2. And then you complain, Letterio, but here the indices are not in decreasing order. Ah, you are right. Well, we change the position. But how can you change the position? Is the same? No, it's not the same. Every time you change the position of two exterior factors, you put a minus in front of. But you cannot say that this yoga is difficult. This is not difficult. Now, what I am going to show you is that exterior powers are very, very concerned with combinatorics, and they are related with very nice notions which have many applications in number theory. In Euler studied, for instance, this subject, or number theory, or combinatorics, theory of symmetric function, and is the notion of partitions. Partitions. Ciao, sto facendo una lezione. A più tardi, ciao. Partitions. What is a partition? A partition is a very easy definition. Is a sequence. Is a sequence. Which is non-increasing, with terms non-negatives, and all zero but finitely many. Oh, what is this? You must give a string of a finite string of number. Let me show you an example of partition. Example. 4, 4, 3, 2, 1, 0, 0, 0, 0, 0 is a partition. Okay? 2, 3 for us is not a partition because we are not respecting the non-increasing order, but there is the French school which use the increases order. So this is no partition in our framework. Sorry, in our framework. And 3, 2, 1, 0, 0, 0 is a partition. Partition. But after 3, 2, 1, we have 0, 0, 0, and I put just 3, but I should put infinitely many. And we don't want to put infinitely many zeros, also because we are not able to put infinitely many zeros, because we would need an infinite long life. So we just record the elements which are not 0. So, therefore, 4, 4, 3, 2, 1 is a partition. And 4, 2, 1 is a partition. And you say, but partition of what? Why partition? Partitions of what? Definition. Let P for all, but okay, so let me write better. Oops. Let me write better. Let P be the set of all partitions. Partition lambda 1 bigger than lambda 2, bigger than lambda 3, and so on, has length, this is the length, as length r if lambda r plus 1 is equal to 0. And then lambda r plus 2 is 0 as well, because they are non-increasing. So the length of the partition lambda is the number of I such that lambda I is not 0. So for instance, this is a partition of length 5. 4, 4, 3, 2, 1 is a partition of length 5. 4 to 1 is a partition of length 3. Or I am used to denote by PR lambda in P such that the length is smaller or equal to R. It means that the partition may have R parts, non-zero, but may have also less. For instance, example, 3, 2, 2, 1 belong to P4 because it's a partition whose length, which is 4, is less or equal than 4. Then one say, okay, but then is also a partition belongs to P5. Yes, of course. The fact is that when it's P5, we can also add 1, 0, just to emphasize that we are considering partition with at most 5 parts. And if we consider partition with at most 5 parts, we can also find some 0 elements. Exercise. Let us look for all partitions of length smaller or equal than 3. Very easy. Solution. Just doing the list. Solution. There is, first of all, the 0 partition. 0, 0, 0, 0, 0, as length 0, so smaller than 3. Then we have 1, we have 2, we have 3. we have 4, we have 5, we have infinitely many. But then we have also 2, 1, 2, 2, and 3, 1, 3, 0. I don't put 3, 0 because it's contained here, but I have 3, 1, then I have 3, 2, then I have 3, 3, and then I have also partition like 3, 3, 3, or 3, 3, 2, 3, 3, 1, 3, 2, 1, etc. So they are infinitely many. There are infinitely many partitions with a length smaller or equal than 3. But now I introduce another notion, definition. Let lambda belongs in P, which is a partition. The weight of the partition, the weight of the partition lambda is very easy, is the sum of the parts. And the sum I bigger or equal to 0. Why bigger than 0? Yes, because from a given point beyond, all the parts are 0. Okay? So the weight is the sum of the parts. Okay? Example. Let 3, 2, 2, 1 partition. This is in P4, for instance. The weight of lambda is 3 plus 2 plus 2 plus 1, which is 3 plus 5, 8. 8. Maybe we are going to understand why the partitions are called partition, because they are a partition of the integer corresponding to its weight. Let's do an exercise. I'd like to do this exercise together with you. Are you online?
Yes.
Okay.
Yes.
This is something I'd like to do with some young person in the audience. But exercise. Let us list all the partitions of the integer 3. Let's do this. Okay. I do the exercise for you, but you should do. And then you do 4. It's funny. Look, 3 is a partition of the integer 3. I divide the integer 3 in one part. There is just one part equal to 3. But 3 can be written also as 2 plus 1. So this is another partition of the integer 3. But I have also 1, 1, 1. Look, and I list all the partition of weight of the integer 3. Of course, you can say, well, 2, 1, 0, 0, 0 is also a partition of the integer 3. Yes, but when we have not relevant zeros, we just forget from our notation. Then I'd like to ask to young people, what is the length of this partition? Is 1. What is the length of the partition to 1? Is there somebody like Christine was there? Christine, you want to say me the length of this partition? Do you want?
Yes. Elise is the name.
is there?
Yes, no, the name is Elise.
Elise, forgive me, Elise, because I'm not seeing your name. So, Elise, do you want to say me? The length of this...
Sorry?
The length of this partition. If you forgot, is just counting the number of the parts. Two, and the length of the partition 1, 1, 1.
That is 3.
Very good, very good. So, Elise, let me exploit you a little bit more. Let's compute, list all partitions of 4, of the integer 4. Let's do this. We have the first is 4, then say me another one.
You can have 2.
Very good, very good. 2, 2 is a partition of 4, but if the number, suppose we want to compute the partition of the integer 10, to list the partition of the integer 10, we can do that. But if we don't use some rule to organize the data, we may forget some. So, 2, 2 is okay, but I would put before 3, 1. You know, I lower the first number, and then I try to put what I miss. You understand? And then I look for all the partition of length 2. So what is the next one? The next one is precisely what you said me, 2, 2. And we see that with the length 2, we put all. Can you say me the other one?
Of length 2?
No, length 2 we did already.
Done.
Now length 3.
So you can have 1, 1, 1, 1.
Yes, but this is length 4 already. There is length 3. There is one in length 3.
Okay. You can have 2, 1, 1.
Very good. And then, as you correctly said, 1, 1, 1, 1. Okay? So we have discovered that the number of the partition of the integer 4 is 1, 2, 3, 4, 5. 5. Okay? You know that computing the number of the partitions of an integer is a very interesting problem in number theory. Well, it was solved by Euler, basically, because you know what Euler did. We will not prove this formula, but theorem by Euler say this, that if we use the same trick, we consider Pn is the number of the partition of the integer n, and times Tn, and we consider the sum for all n bigger or equal than 0. I will explain you well how this formula is obtained by studying some very interesting and amusing particular case. But Euler found this beautiful formula. So, this is beautiful because it's saying that this series is the same as this infinite product. Okay? For instance, I claim if pkn tn, if pkn is partitions of length smaller or equal than n, It is fantastic that the sum of pkn tn is just this. 1 minus t, 1 minus t squared, 1 minus t cubed, up to 1 minus t to the power k. And I promise you we will do some exercise on this. For instance, we can see how this formula works for all the partitions of weight, for all the partition of length at least 2. This formula says that if I want to know how many partitions of length at most k of the integer n, is just compute the second member, chase the power of the nth power of t and look at the coefficients. That's just this. The coefficient is the answer. But this now I say to you, I'm not very interested that you grasp now, right now, the meaning of this formula, but I wanted to let you smell that what we are doing is related with very deep mathematics, most of what I don't understand. And maybe we can try to understand all together. But now, all of you say, Letterio, you have no plan, because first you speak about exterior algebra, exterior power, and then partition. What have they to do with us? Okay, then partitions and exterior power. Let's do this first exercise. Let's consider V4 span of B3, B2, B1, B0. Please, let's write a basis of wedge 2, 4. Maybe Elise wants to help me again. Would you like to help me or not? If you don't like me, you just say, no, I don't like you. Would you like to help me, Elise? I want the basis of this. I would do B3 wedge B2, B3 wedge B1, B3 wedge B0, B2 wedge B1, B2 wedge B0, and B1 wedge B0, right? Is it okay? Elise?
Yes.
Okay. Now, I want to show you this. I want to show that all the basis elements can be obtained by the first one. Because B3 wedge B2 can be written as B1 plus 2 wedge B0 plus 2. Now let's go to B3 wedge B1. Elise, help me. I want to write B1 plus 2 wedge B0 plus
1.
Very good. And then let me do B2 wedge B1. B2 wedge B1, we want to write B2 as B1 plus 1 wedge B0 plus 1. That is, all the elements can be obtained by adding something to 1 and 0 in such a way that the sequence of the indices is decreasing. But then we discovered that this element is showing me the action of the partition 2, 2. And here there is the partition 2, 1. And here there is the partition 1, 1, 0. No, sorry, 1, 1. 1, 1. Then, okay, we have discovered that wedge 2v4 is the span of B1 plus lambda 1 wedge B0 plus lambda 2, where lambda 1 bigger or equal than lambda 2, bigger or equal than 0, is a partition. Yeah, but this cannot be all the partition. Cannot be all the partition, because if lambda 1 were 3, B1 plus lambda 1 would be before. We have not before there. But it is easy to describe because we can consider the Young diagram of a partition. The Young diagram of a partition is the Young diagram of partition is just this. Example. Consider the partition 3, 3, 2, 1, 1. Okay, this is a partition with 5 parts, and then for each part the first part is 3, and we construct a diagram of 3 boxes. Then there is the second part, which is 3. And we put 3 boxes downstairs, and then 2 boxes after the 3, and then 1 box. Is it difficult, this? Who is thinking that this is difficult? Let's see the partition 2, 1. 2, 1 is just this. And there are people that just confuse partition with the Young diagram. And what is this? This is the partition 1, 2, 3, 4, 5, 5, 3, 1, 1. Okay? So in our case, then wedge 2v4 in our exercise possesses a basis formed by all the partitions contained in a 2 times 2 square. What does it mean, this? It means this. You see this square? You see this square? This square? This square, you say, this square is the partition 2, 2. Yes, the partition 2, 2 is one of these partitions. And first of all, there is a partition where you don't color any square. So there is the partition 0. Partition 0. Then there is the partition 1. It's a partition 1, just 1. But there is also the partition 2. But there is also, maybe I write the diagram downstairs. This is nothing. This is the partition This is the partition. And now we have also the partition 1, 1. As you see, is contained in 2 by 2 square. And then we have also the partition, this one. This is the partition 2, 1. And then finally, you have also the partition. Oh, let's count how many diagrams we have depicted. We have 1, 2, 3, 4, 5, 6. Exactly 6. Look at the basis. Look at the basis of wedge 2 before. Where is the basis? 1, 2, 3, 4, 5, 6. So it means that exterior powers possesses bases parameterized by partitions. It means in general, you see, I'm not doing much theory, I'm doing more exercise, but in general, wedge KVN possesses a basis parameterized by all partitions of length at most k, because you see, here we have considered wedge 2V, and this is partition of length 1, not of length 2, but this is at most 2, contained in a k times n minus k rectangle. Here the most useful thing to do here is doing exercise. Maybe we can organize an exercise session for people who wants, because there is no way to understand well these things than doing experiments. For instance, experiment. Basis of wedge 3V5. Okay? So it means that we have to consider all the partition of weight 3 contained of length at most 3 contained in a 2 times in a 3 times 5 minus 3 rectangle. I put this, now we can count. Look, now I count the dimension wedge 3, 5. I count by counting the partition. Okay, I have first the partition 0. Then I have the partition 1. Then I have the partition 2. Then I have a partition 3. Good. Now I have the partition, and I found already 4. Then I have the partition 1, 1. Then I have the partition 2, 1. Then I have the partition 3, 1. And then I have 3 more partition. Then I have the partition 2, 2, 2. And then 3, 2 plus 2. And finally, I have no choice, the partition 3, 3. And this one more partition. And I count 1 plus 2 is 3. Plus 3 is 6. Plus 4 is 10. Let's compute 5 choose 3 is the same as 5 choose 2. 5 times 4 over 2 is 10. It's beautiful, it's beautiful. The binomial coefficients coincide with the number of partitions contained in n and k times n minus k rectangle. This is very relevant because this permits you to transform algebra in combinatorics, in a game that even children can play, you know? So for us will be relevant that exterior powers have a basis parameterized by partitions. This is very relevant, and the reason why this is important is that if you take the ring B2 Q E1 E2, this is a ring in two indeterminates. This ring is isomorphic as a vector space to wedge 2V, where V has infinite dimension. I mean, V is the sum Q Bi, I bigger than 0. Now I'm going to stop, but I want to explain you the reason why there should be this isomorphism, because next time, or when you ask me, I want to convince you that if you take a ring of polynomial, they possess a basis formed by partitions of length. I mean a ring of polynomial in two indeterminates. This ring possesses a basis formed by partitions of length at most 2. Okay? You say, well, I know already a basis of this vector space are all the monomial. The monomial, of course. A polynomial there is a linear combination, is finite linear combination of monomial. The monomial are like this. So what I should do for you is to teach you how to associate to such a monomial a partition of length 2. When I show that this gives me a partition, that partition corresponds also to an element of the exterior power. And then the two things are isomorphic, as abstractly as a vector spaces. And we will see that this is the very roots of what physicists call the correspondence between bosons and fermions. Okay, so with our games, we can smell some higher mathematics. I would stop here, but for next time, I would like to stop going on with the theory and making only exercise to familiarize to what we did up to now. I want to depict Young diagrams, to compute the basis of exterior power, of exterior algebra, doing some exercise in linear algebra, just because I want you walk on firm ground. Okay? Any question?